North Africa, November 1942. The first reports filtering back from Operation Torch painted a confused picture of Allied progress, but one detail began to coalesce. German forces, though outmatched in some areas, were deploying an unexpected and irritating obstacle. Initial encounters with these devices, hastily described by forward elements, suggested rudimentary construction, a crude approach to battlefield denial that American engineering detachments, accustomed to their own sophisticated demolition technologies, initially found almost comical. The stakes were immediate and tactical: slowed advances, diverted supply lines, and an erosion of momentum in critical sectors. Lieutenant Colonel Arthur Vance, a veteran of the Army Corps of Engineers with a specialization in ordnance and explosive countermeasures, reviewed the initial intelligence summaries with a practiced eye. His team, based at a temporary forward analysis center near Oran, had begun to receive physical examples of these German mines. The first specimen, designated by intelligence as a teller mine, arrived in a sand-caked crate, its basic form immediately apparent. Vance noted its simple, circular steel casing, roughly 32 centimeters in diameter and 10 centimeters high, weighing approximately 9 kilograms. He observed the pressure plate, a large, slightly convex disc dominating the top surface, and the 3 fuse pockets, protected by screw-in caps. Disassembly revealed a straightforward internal mechanism. A main charge of TNT, typically 5.5 kilograms, occupied the bulk of the casing. The primary fuse, a TMIZ-35, was a mechanical pressure-activated device requiring a downward force of approximately 90 to 120 kilograms to initiate. This threshold, Vance calculated, was well above that exerted by an individual soldier, but perfectly calibrated for the weight of a vehicle. The casing itself was stamped steel, welded together, lacking the precision-machined components common in American anti-tank ordnance. The manufacturing process appeared to prioritize speed and material economy over intricate design. Vance compared it to the M1 anti-tank mine, the standard American equivalent. The M1, while effective, was a more complex assembly, featuring a bakelite casing, a chemical delay fuse, and a more intricate arming mechanism. Its production required specialized plastics and a finer degree of assembly line precision. The German teller mine, by contrast, seemed almost agricultural in its simplicity, a brute force solution. The initial assessment within Vance's team was that this was a stopgap measure, an unsophisticated device born of wartime exigency rather than deliberate engineering prowess. Its widespread deployment, however, suggested a different reality, one that would soon challenge their assumptions about battlefield effectiveness. The sun-baked tracks of North Africa, 1942. Allied forces, advancing with a newfound confidence after initial setbacks, began to encounter an insidious new threat. It was not the familiar, precisely laid German anti-tank mine, nor the often haphazard Italian emplacements. Instead, a series of catastrophic vehicle losses began to plague supply convoys and forward reconnaissance patrols, leaving behind a trail of mangled steel and bewildered engineers. The first reports filtered back from the desert, describing trucks ripped apart, their chassis twisted into unrecognizable forms, often with the entire front axle assembly launched meters from the blast crater. Initial assessments by ordnance disposal teams pointed to a peculiar type of detonation, far more powerful than the standard Tellermine 35 or 42. The craters were deep, often 2 to 3 meters across, and exhibited a distinct conical profile, indicative of a large, concentrated charge buried at a significant depth. Recovery efforts were hampered by the sheer violence of the explosions. Often, little remained of the vehicle, save for fragmented components scattered over a wide radius. Forensic analysis of blast sites, meticulously documented by Royal Engineer detachments and later by American EOD teams, revealed consistent patterns. The charges were almost universally buried beneath the main tracks of desert roads or at critical choke points in wadis. Unlike factory-produced mines, these devices showed no uniformity in casing or fuse mechanism. Some were housed in repurposed oil drums, others in wooden crates, and a few in sections of discarded pipe. The explosive filler, identified through residue analysis, was often a crude mixture of locally sourced nitrates and fuel oil, or sometimes captured Italian or French artillery shells, their fuses removed and replaced with improvised detonators. The triggering mechanisms were equally rudimentary but brutally effective. Pressure plates fashioned from scavenged metal sheets or even thick planks of wood, connected to simple crush fuses or pull igniters, were common. One particularly insidious design involved a spring-loaded striker held in tension by a thin wire, designed to snap and detonate a blasting cap when a vehicle's weight depressed the plate. The lack of metallic components in many of these fuses rendered standard electromagnetic mine detectors largely ineffective, forcing engineers to resort to slow, painstaking manual probing, a process both dangerous and time-consuming. The sheer volume of explosive material, often 50 to 100 kilograms, far exceeded the typical 5 to 10 kilograms found in conventional anti-tank mines. This overcharge, coupled with the deep burial, created a powerful belly blast effect, directly impacting the underside of vehicles where armor was thinnest. Damage reports from the British 8th Army indicated a 400% increase in irreparable vehicle losses due to mine incidents in certain sectors during late 1942, a statistic that began to alarm high command. The psychological impact on drivers and convoy personnel was profound. The knowledge that a crude, undetectable device could obliterate a truck and its occupants without warning fostered a pervasive sense of dread. The strategic implication of these crude mines extended beyond mere vehicle destruction. They effectively slowed Allied advances, forcing engineers to clear routes inch by painstaking inch, often under sporadic sniper fire. Supply lines became vulnerable, and the need for dedicated mine-clearing units, equipped with more robust and innovative detection methods, became critically apparent. This rudimentary weapon, dismissed initially by some as the desperate measure of an outmatched foe, was proving to be a formidable and adaptable instrument of attrition, challenging the very assumptions of modern mechanized warfare. The captured German mines, particularly the Tellermine 43 and the Schuhmine 42, underwent rigorous examination at Allied proving grounds. Engineers, initially dismissive, quickly recognized the deceptive simplicity and inherent lethality of these devices. The Tellermine 43, a circular anti-tank mine, comprised a pressed steel casing, 32 centimeters in diameter and 10.2 centimeters high, containing 5.5 kilograms of TNT. Its most striking feature was the central pressure plate, designed to withstand incidental pressure but activate reliably under the weight of a vehicle. This pressure plate, a dished steel disc, rested on a spring-loaded igniter assembly. A force exceeding 100 kilograms, typically applied by a vehicle's tire or track, depressed the plate, shearing a safety pin and driving a striker into a percussion cap. The resulting flash ignited a detonator, which in turn initiated the main TNT charge. This direct mechanical action, devoid of complex electrical circuits or delicate chemical delays, made the mine remarkably robust and resistant to environmental factors. Its flat profile also allowed for shallow burial, making detection more challenging. In contrast, the Schuhmine 42, an anti-personnel device, presented a different kind of engineering challenge. It was constructed almost entirely from wood, a material chosen not for cost saving alone, but for its non-metallic properties. A simple wooden box, approximately 13 centimeters long and 10 centimeters wide, contained 200 grams of TNT. The pressure plate, also wooden, was hinged at one end and held aloft by a small wooden block. When a foot pressed down on the plate, the wooden block collapsed, allowing the plate to descend and activate a rudimentary igniter. This igniter, Often a simple friction igniter or a chemical delay fuse then detonated the TNT. The absence of metal components rendered the shoe mine virtually invisible to early electromagnetic mine detectors, a significant tactical advantage. Damage reports from forward units indicated a disproportionate number of foot injuries and non-fatal casualties designed to degrade unit cohesion and medical resources rather than achieve outright kills. The strategic implication of these designs was profound. The Tellermine 43, with its robust construction and substantial explosive charge, was a direct threat to armored columns, capable of immobilizing or destroying tanks and half-tracks. Its simplicity meant rapid mass production, with German factories churning out hundreds of thousands annually. The shoe mine 42, on the other hand, exemplified a more insidious form of warfare, exploiting the limitations of existing countermine technology and imposing a psychological burden on infantry. The sheer volume and diverse application of these mines forced a reevaluation of Allied engineering priorities and countermine doctrine. The German engineers, operating under the ever-tightening constraints of a wartime economy, had long since abandoned the pursuit of elegant solutions. Their focus had shifted entirely to utility, to the rapid deployment of effective obstacles with the fewest possible strategic materials. The initial laughter from Allied engineers, predicated on the perceived crudeness of early German mine designs, had begun to curdle into a grim acknowledgement of their efficacy. One such design, the Tellermine 43, exemplified this stark pragmatism. Its casing, a simple stamped steel dish, was pressed from sheet metal, a material readily available from numerous civilian manufacturing lines. The internal components were equally austere: a main charge of trinitrotoluene, typically 5.5 kilograms, and a pressure-activated fuse mechanism. This fuse, often the weakest link in early mine designs, was deliberately simplified, relying on a spring-loaded striker and a sensitive primer, all housed within a bakelite cap. Production figures for the Tellermine 43, gleaned from captured ordnance logs, indicated a staggering output. By late 1944, factories were reporting daily yields exceeding 20,000 units, a rate far surpassing the complex manufacturing processes required for Allied anti-tank mines like the M1A1. The simplicity of its design allowed for decentralized production, with smaller workshops and even converted agricultural machinery plants contributing to the overall volume, a stark contrast to the highly specialized facilities required for more sophisticated munitions. This mass production, coupled with the mine's low profile and robust construction, transformed it from a mere nuisance into a significant tactical impediment. Allied damage reports from the Western Front, particularly during the Ardennes offensive, frequently cited the Tellermine 43 as the primary cause of vehicle attrition in forward areas. A single mine strike could disable a Sherman tank, severing its tracks and often detonating secondary ammunition, rendering the vehicle a total loss. The strategic implications were profound. Each disabled vehicle represented not just a material loss, but a disruption to logistics, a delay in advance, and a drain on recovery assets. The psychological impact on drivers and tank crews, knowing that any stretch of unpaved road or even seemingly benign field could conceal such a potent threat, was an unquantifiable but tangible factor in the slowing of offensive operations. The crude, stamped metal disc, once dismissed, had become a silent, pervasive arbiter of battlefield momentum. Normandy, June 1944. The initial Allied advance, characterized by rapid armored thrusts and infantry exploitation of breakthroughs, began to encounter a new and insidious resistance. Road networks, once avenues of swift progress, became choke points of destruction, forcing a reevaluation of established tactical doctrine. The engineers, who had once dismissed the crude devices, now faced the tangible consequences of their underestimation. Damage reports from the front lines, compiled daily by ordnance and recovery units, painted a stark picture. Within the first 2 weeks of sustained engagement, over 400 Allied vehicles, predominantly trucks and light armored cars, sustained catastrophic damage attributed directly to these improvised explosive devices. These were not merely immobilized vehicles. The force of the detonation often ripped axles clean from chassis, buckled frames beyond repair, and incinerated cargo. The logistical tail of the invasion, already stretched, began to fray under the cumulative attrition. A close examination of recovered fragments and crater analysis revealed the consistent signature of the Teller mine, or its locally produced variations, often augmented with secondary charges. The standard German Teller mine, the TMI-43, contained 5.5 kilograms of TNT, sufficient to rupture a tank track or disable a wheeled vehicle. However, the mines now encountered frequently exceeded this, with some improvised devices containing up to 10 kilograms of explosive, often packed into repurposed artillery shells or even wooden crates, deliberately designed to defeat the underbelly protection of even medium tanks. The pressure plates, often made of wood or thin metal, were designed for a minimum pressure of 200 kilograms, ensuring detonation only under the weight of a vehicle. Production logs from German field workshops, later captured, indicated a surge in anti-tank mine fabrication following the Normandy landings. While dedicated factories produced millions of standardized Teller mines, local units were encouraged to improvise, utilizing readily available materials and captured Allied ordnance. This decentralized production model, initially seen as a weakness, proved remarkably resilient, allowing for rapid adaptation to local terrain and target profiles. The sheer volume, coupled with the varied construction, made detection and neutralization an increasingly complex and dangerous task. The strategic implication was profound. The pace of the Allied advance, critical for maintaining momentum and exploiting tactical advantages, was perceptibly slowing. Supply convoys, vital for sustaining the front lines, were forced to adopt circuitous routes, increasing travel times and fuel consumption. Engineers, previously focused on bridge building and obstacle clearance, now found themselves embroiled in a constant, deadly game of mine detection and disposal, often under direct fire. The initial laughter had long since faded, replaced by a grim determination born of necessity. The Western Desert, late 1941. British patrols, accustomed to the predictable patterns of Italian minefields, began encountering something new. These were not the carefully laid, uniformly spaced obstacles of conventional doctrine, but rather chaotic concentrations, often found in unexpected places, creating a disorienting effect that defied established clearance procedures. German ingenuity, under the pressures of rapid maneuver warfare, had turned the mine from a static defensive barrier into a dynamic, almost offensive weapon. The Teller mine, specifically the Teller mine 35 and later the 42, represented the core of this shift. Its casing, initially pressed steel, later simplified to a bakelite or even concrete body, housed a main charge of 5.5 kilograms of TNT, sufficient to disable the track or even shatter the bogie wheels of a medium tank. The pressure plate, a simple but effective mechanism, required a sustained force of 100 to 200 kilograms to detonate, ensuring it would not be triggered by infantry, but would reliably respond to the weight of a vehicle. Production figures from German ordnance factories, documented in captured industrial reports from 1942, showed a dramatic escalation in output. While early war production averaged around 50,000 Teller mines per month, by mid-1942, this had surged to over 300,000 units monthly, a six-fold increase driven by simplified designs and mass production techniques. This scale of output allowed for tactical deployment far beyond the traditional defensive line. The real innovation, however, lay not just in the mine itself, but in its deployment. Specialized mine-laying vehicles, such as the Minenwerfer, based on the SDKFZ 251 half-track, could scatter mines at speed, often under fire, creating instant, albeit crude barriers. Even more disruptive were the improvised methods. Mines were dropped from low-flying aircraft, rolled from the backs of trucks, or even hand-thrown in the chaos of a retreat. The effect was less a minefield and more a mine-saturated zone, designed to deny ground and channel enemy movement, rather than simply destroy individual vehicles. This rapid, almost indiscriminate deployment challenged the meticulous, slow-paced methods of Allied mine clearance. British and American engineers, trained to methodically probe and disarm, found themselves overwhelmed by the sheer volume and unpredictable placement of these new obstacles. The psychological impact was profound. Every stretch of open ground became suspect, every advance slowed by the unseen threat. The laughter at crude German engineering had ceased, replaced by a growing apprehension. The aftermath of the initial encounters, the mangled chassis and shattered axles, forced a grudging reevaluation. Damage reports, meticulously compiled by ordnance specialists, began to paint a consistent picture. A low-yield, high-impact event, often beneath the vehicle's center of gravity. The sheer simplicity of the devices initially fostered a dismissive attitude among some American engineering teams, accustomed to the precision of factory-produced munitions. They had observed the crude constructions, the often improvised casings, and the seemingly random placement, and had, in early assessments, characterized them as more nuisance than threat. This initial underestimation stemmed from a deeply ingrained engineering philosophy, one that prioritized standardization, predictable performance, and a clear chain of design and production. The mines encountered in the field defied these expectations. They were not uniform. Their explosive charges varied widely, from repurposed artillery shells to blocks of commercial dynamite, often initiated by crude pressure plates fashioned from wood or scrap metal. The detonation mechanisms, too, were a study in ad hoc ingenuity, ranging from simple contact fuses to more complex, if still rudimentary, tilt switches. The quantitative impact, however, began to shift perceptions. Unit diaries from the 1st Infantry Division recorded 14 vehicle losses and 37 personnel casualties attributed to these devices in a single 2-week period in late 1943. While not on the scale of major combat engagements, these were losses sustained outside direct fire, often on supposedly secure supply routes. The cumulative effect on logistical operations was disproportionate to the individual incidents. A single disabled truck could halt a convoy for hours, creating choke points vulnerable to further attack, or delaying critical resupply efforts. The strategic implication of these seemingly primitive weapons began to emerge with chilling clarity. They denied terrain, not through direct occupation, but through the imposition of risk. Roads and tracks, once considered safe avenues of advance or retreat, became zones of uncertainty. The psychological toll on drivers and convoy commanders was palpable. Every bump, every shadow, became a potential trigger. This forced a reallocation of resources, diverting combat engineers from offensive tasks to the laborious, dangerous work of mine clearance, often under harassing fire. The ideological clash was subtle but profound. American doctrine emphasized overwhelming firepower and technological superiority. These crude mines, however, demonstrated that effective resistance could be mounted with minimal resources, exploiting vulnerabilities rather than matching strength. They were an asymmetric challenge, forcing a reevaluation of what constituted a weapon and how a technologically advanced force could be effectively countered by ingenuity and adaptation. The laughter had ceased, replaced by a quiet, unsettling recognition of a new kind of warfare. The improvised explosive device, once a curiosity of insurgent desperation, evolved into a pervasive and lethal instrument of attrition. Early Allied assessments, often tinged with a dismissive professionalism, underestimated the cumulative effect of these crude mines. The initial laughter of engineers, born of a perceived technical superiority, faded as vehicle losses mounted and operational tempo faltered. These devices, ranging from repurposed artillery shells to simple charges of fertilizer and fuel oil, were not sophisticated in their construction, but devastating in their application. Their ubiquity stemmed from their low cost, readily available components, and the ease of their deployment by local populations familiar with the terrain. A single detonation, while perhaps not always destroying a heavy tank, could disable it, block a road, and create a tactical bottleneck. Damage reports from the European theater, compiled between 1944 and 1945, illustrate a stark shift. While purpose-built anti-tank mines remained a significant threat, the category of improvised explosive devices, or roadside bombs, began to account for an increasingly substantial percentage of vehicle casualties, particularly among lighter transport and logistical convoys. For every purpose-built teller mine encountered, intelligence summaries indicated 3 to 5 instances of a vehicle striking a locally fabricated charge. This escalating threat forced a reevaluation of Allied doctrine. Initial responses focused on increased mine-clearing operations, but the sheer volume and dispersed nature of these devices made comprehensive clearance impossible. The emphasis shifted to vehicle hardening and route reconnaissance, with dedicated engineering units assigned to lead convoys, meticulously scanning for disturbed earth or unusual objects. Vehicle design, too, began to reflect this new reality. While the war concluded before widespread implementation, post-war development saw a greater emphasis on V-shaped hulls and elevated chassis, specifically designed to deflect blast forces upwards and away from the crew compartment. The lessons learned from trucks being launched off-roads by crude charges directly informed these structural modifications, transforming what was once considered a minor nuisance into a primary design consideration for future armored personnel carriers and logistics vehicles. By 1950, the first production models of the M59 armored personnel carrier incorporated these blast-resistant features, a direct lineage traceable to the improvised threats of the preceding conflict.